In Orbit Wars, the objective is to capture territory across a multi-agent 100 by 100 continuous coordinate space. Success is governed by an uncompromising execution limit, exactly 1 second per turn. Faced with a complex simulation, the immediate reflex for many developers is to deploy a massive deep reinforcement learning model to solve the environment. That approach fails quickly. The time required for neural network inference, just to process the board and output a single action, consumes the entire time budget before any deep planning can occur. Instead, the competitive field relies on hyper-optimized software engineering and rigorous game theoretic search. Achieving advanced behavior in this environment requires a departure from standard machine learning. You reach high-level play by foregoing neural networks entirely. This interface from the 2010 Google AI Planet Wars Challenge defines the historical lineage of the game. In this predecessor, planets functioned as fixed nodes with static travel distances. Because planets were permanent anchors, simple graph search algorithms could calculate the exact time to arrival and required ship counts with perfect certainty. Legacy agents succeeded using basic heuristic logic based on these fixed, predictable integers. Orbit Wars replaces that static stability with a continuous coordinate space where targets are in constant, nonlinear motion. The complexity is further increased by variable fleet speeds that scale logarithmically with ship count, and a central solar hazard that destroys any fleet entering its radius. Moving from discrete graph logic to continuous spatial movement breaks legacy models, making a ground-up rebuild of the local simulator a technical necessity. The foundational technical hurdle for the agent simulator is solving the continuous orbital intercept calculus. Inner planets rotate at a constant angular velocity, following a predictable arc around the central sun. If an agent launches a fleet directly at a planet's current coordinates, it misses. The target rotates away, and the ships arrive in empty space. To hit the target, the agent uses rotational transforms to determine the planet's exact coordinates at the future moment of fleet arrival. This calculation adjusts for fleet size. Because larger swarms travel at higher velocities, the intercept angle changes with every single ship added to the launch. The agent then runs continuous line segment collision detection to ensure the projected flight path does not intersect the lethal radius of the sun. Without this mathematically rigorous continuous time model, the agent suffers from travel time blindness, rendering any higher-level strategy unusable. To look ahead effectively, the agent's forward simulator must process 200 to 500 future turns every second. Standard object-oriented Python is too slow for this task. Iterating over individual planet and fleet objects with for loops introduces excessive computational latency. Reaching this speed necessitates replacing Python objects with pure NumPy vectorization. This aligns disparate elements, comet expiration, orbital rotation, and fleet movement into uniform matrix operations. Deterministic combat is then calculated across all planets simultaneously in one matrix update. This pure math engine is what enables the agent to explore deep forward search trees while remaining under the 1 second limit. Layered on top of the physics engine is the core decision-making algorithm, Monte Carlo Tree Search, or MCTS. During the selection phase, the agent decides which potential future actions to simulate first. The search is guided by the upper confidence bound formula, balancing the exploitation of high win rate moves against the exploration of untested branches. This exploration parameter forces the algorithm to evaluate deeper tactical branches, preventing it from getting stuck on surface-level moves. When the algorithm reaches a leaf node, it triggers a rollout, simulating the game to completion to determine the outcome. Executing purely random actions during this phase produces noisy, unusable data that corrupts the logic of the search tree. The solution is to inject a hard-coded heuristic policy. This forces the rollout to make logical moves by ranking targets based on their production value divided by travel time. This injection allows high-fidelity evaluation signals to backpropagate to the root, enabling the agent to reliably discover complex, multi-way snipe maneuvers. The final architectural layer involves removing human guesswork from the heuristic rollout parameters. Because the simulator is CPU-based and highly optimized, engineers can run thousands of concurrent bot versus bot games locally without needing expensive cloud GPU clusters. This topographical map represents the covariance matrix adaptation evolution strategy, or CMAES. It fine-tunes the agent by testing thousands of variations against each other. The system mutates specific weights across generations: production value, defensive buffers, and aggression thresholds. Through continuous days of self-play evaluations, the system iterates until it converges on a mathematically optimal parameter weighting. By layering evolutionary tuning over an MCTS algorithm, driven by vectorized spatial physics, the engineer converts a restrictive 1-second timeout into a predictable strategic advantage.